Welcome. Today we're diving into the fascinating world of the periodic table, focusing on two key trends: atomic size and ionization energy. These trends help us understand why elements behave the way they do and how their properties change across the table. By visualizing these patterns, we can make sense of the periodic table's layout and predict the behavior of elements. Whether you're a student, a science enthusiast, or just curious, this journey will make periodic trends clear and memorable. Let's start by exploring what the periodic table actually represents and why these trends matter in chemistry. Periodic table is more than just a chart of elements. It's a powerful tool that organizes all known chemical elements based on their atomic number, electron configuration, and recurring chemical properties. Each row is called a period, and each column is a group or family. The arrangement reveals patterns or trends that repeat across the table. These trends are not random, they're rooted in the structure of atoms and the way electrons are arranged. Understanding the periodic table's structure is the first step to unlocking the secrets of atomic behavior. The heart of the periodic table is the atomic number, which tells us how many protons are in an atom's nucleus. As you move from left to right across a period, the atomic number increases by 1 with each element. This increase affects the element's properties, including its size and how tightly it holds onto its electrons. The atomic structure, especially the arrangement of electrons in shells, is key to understanding why trends like atomic size and ionization energy exist. Atomic size, also called atomic radius, is a measure of how large an atom is. It's typically defined as the distance from the nucleus to the outermost electron shell. Atomic size isn't fixed, it can change depending on the atom's environment and its position in the periodic table. By comparing atomic sizes, we can see clear patterns that help explain chemical reactivity and bonding. As you move down a group in the periodic table, atomic size increases. This happens because each new period adds another electron shell, making the atom larger. Even though the number of protons increases, the added shells outweigh the increased nuclear charge, so the outer electrons are farther from the nucleus. This trend is easy to visualize. Think of each row as adding another layer to the atom. Moving from left to right across a period, atomic size actually decreases. Why? As you add more protons to the nucleus, the positive charge increases, pulling electrons closer in. Even though you're adding electrons, they're going into the same shell, so the atom gets smaller. This shrinking effect is a key trend that helps explain why elements on the right side of the table are generally smaller than those on the left. Let's visualize atomic size with a simple animation. Imagine each atom as a circle and watch how the circles get bigger as you move down a group and smaller as you move across a period. This visual approach makes it much easier to remember the trend and see how atomic structure shapes the periodic table's layout. While the general trends for atomic size are reliable, there are exceptions. For example, transition metals in the center of the table don't always follow the same pattern because of how their electrons are arranged. These exceptions remind us that chemistry is full of interesting details and that trends are helpful guides, not absolute rules. Ionization energy is the energy required to remove an electron from an atom in its gaseous state. It's a measure of how tightly an atom holds onto its electrons. High ionization energy means the atom holds its electrons tightly, while low ionization energy means they're easier to remove. This property is crucial for understanding chemical reactivity and bonding. As you move from left to right across a period, ionization energy increases. This is because the atoms are getting smaller and the nuclear charge is stronger, so electrons are held more tightly. It takes more energy to remove an electron from these atoms. This trend helps explain why elements on the right side of the table, like noble gases, are so stable and unreactive. Moving down a group, ionization energy decreases. Atoms get larger and their outer electrons are farther from the nucleus. The increased distance and shielding from inner electrons make it easier to remove an electron. This is why elements at the bottom of a group like cesium are much more reactive, they lose electrons easily. To help you remember the trend, picture a graph where ionization energy rises as you move right across a period and drops as you go down a group. Visual animations can make these patterns stick in your mind, showing how the periodic table's structure influences atomic behavior. Just like with atomic size, there are exceptions to the ionization energy trend. For example, elements with full or half-full subshells can have slightly higher ionization energies than expected. These exceptions are due to the stability provided by certain electron arrangements. Chemistry is full of these fascinating details that make the subject so interesting. Now let's compare the two trends side by side. As atomic size increases, ionization energy generally decreases and vice versa. This inverse relationship is rooted in the way electrons are held in atoms. Smaller atoms hold their electrons more tightly, requiring more energy to remove them. Larger atoms with electrons farther out let go of electrons more easily. Understanding periodic trends isn't just academic, it's practical. These trends help chemists predict how elements will react, what compounds they'll form, and even how materials behave in real-world applications. From batteries to medicines, periodic trends are at the heart of modern chemistry and technology. Electron configuration, the way electrons are arranged in shells and subshells, plays a central role in periodic trends. Elements with similar configurations are grouped together and their properties reflect these similarities. For example, noble gases all have full outer shells, making them stable and unreactive. This organization is what gives the periodic table its predictive power. Imagine each atom as a series of concentric circles, with each circle representing an electron shell. As you move down the table, more circles are added, making the atom larger. This simple visual can help you remember why atomic size increases down a group and how electron configuration shapes trends. The shielding effect is another key concept. Inner electrons block the attraction between the nucleus and outer electrons, making it easier for those outer electrons to be removed. As you move down a group, the shielding effect increases, which is why ionization energy drops and atomic size grows. Effective nuclear charge is the net positive charge experienced by outer electrons. As you move across a period, the effective nuclear charge increases, pulling electrons closer and shrinking the atom. This concept helps explain why atomic size decreases and ionization energy increases across a period. Let's bring these trends to life with an animation. Watch as atomic size balloons out down a group and contracts across a period while ionization energy does the opposite. Seeing these changes in motion makes the patterns much clearer and easier to remember. Alkali metals found in Group 1 are known for their large atomic size and low ionization energy. This makes them highly reactive, especially with water. Their single outer electron is easily lost, leading to vigorous chemical reactions. These properties are a direct result of their position on the periodic table. Halogens in Group 17 have small atomic sizes and high ionization energies. They are very reactive, but in a different way from alkali metals, they tend to gain electrons rather than lose them. Their high reactivity and unique properties make them essential in many chemical processes. Noble gases, found in Group 18, are unique because they have full outer electron shells. This gives them very high ionization energies and makes them almost completely unreactive. Their stability is a perfect example of how electron configuration shapes periodic trends. Transition metals, located in the center of the periodic table, often show less obvious trends in atomic size and ionization energy. Their unique electron arrangements lead to interesting properties such as variable oxidation states and colorful compounds. These elements are essential in industry and technology. Lanthanides and actinides found at the bottom of the periodic table have their own unique trends. Their atomic sizes and ionization energies are influenced by the filling of f orbitals, leading to subtle variations. These elements are important in specialized applications from electronics to nuclear energy. Periodic trends directly influence how elements react. Elements with low ionization energies tend to lose electrons and form positive ions, while those with high ionization energies tend to gain electrons. This explains why sodium reacts explosively with water while chlorine forms salts by gaining electrons. You might be surprised to learn that periodic trends affect everyday life. From the batteries in your phone to the medicines you take, understanding how elements behave helps scientists design better products. The periodic table is more than just a classroom tool, it's a guide for innovation. Let's recap atomic size visually. Remember, atomic size increases as you move down a group and decreases as you move across a period. This simple pattern is one of the most important takeaways from the periodic table, and it helps explain many chemical behaviors. Now, let's summarize ionization energy. It increases as you move right across a period and decreases as you move down a group. This trend is the opposite of atomic size, and it's just as important for predicting how elements will react. Let's put your knowledge to the test. If you look at potassium and calcium, which one has a larger atomic size? Based on the trends, potassium is larger because it's to the left of calcium in the same period. Practicing with real examples helps reinforce these concepts. Here's another example. Compare sodium and magnesium. Which has the higher ionization energy? Magnesium does because it's to the right of sodium in the same period. Working through these comparisons helps you master periodic trends. Color-coding the periodic table is a great way to visualize trends. For example, you can shade elements with larger atomic sizes in one color and those with higher ionization energies in another. This makes patterns stand out and helps you remember them more easily. The periodic table shows other trends too, like electronegativity and electron affinity. While today we're focusing on atomic size and ionization energy, remember that the table is full of patterns that help explain the behavior of all elements. Periodicity, the repeating patterns in the periodic table, is what makes chemistry predictable. Once you understand the trends, you can anticipate how unknown elements might behave or why certain reactions happen the way they do. This predictability is the magic of the periodic table. Periodic trends aren't just for textbooks, they shape the modern world. From designing new materials to developing sustainable energy solutions, scientists rely on these trends to solve real problems. The periodic table is a living tool, constantly guiding discovery and innovation. To sum up, atomic size increases down a group and decreases across a period, while ionization energy does the opposite. These trends are rooted in atomic structure and electron configuration. Understanding them gives you a powerful framework for predicting chemical behavior. A helpful tip: use mnemonics or visual aids to remember the trends. For example, think of atomic size as balloons getting bigger down the table and ionization energy as a mountain that gets steeper to the right. These mental images can make the trends stick. It's easy to mix up the trends, especially when you're first learning them. Remember, atomic size and ionization energy move in opposite directions. If you ever get confused, go back to the basics. Think about electron shells and nuclear charge. If you're interested in learning more, explore trends like electronegativity, metallic character, and electron affinity. Each of these follows its own pattern across the periodic table and adds another layer to your understanding of chemistry. The periodic table continues to evolve as new elements are discovered and our understanding of atomic structure deepens. It's a living document reflecting the ongoing progress of science. Staying curious and open to new discoveries is key to mastering chemistry. There are many interactive tools and animations online that let you explore periodic trends visually. Using these resources can make learning more engaging and help reinforce the patterns we've discussed today. Periodic trends aren't just theoretical, they have real-world applications. For example, understanding ionization energy is crucial in designing semiconductors, while atomic size matters in creating new materials. These trends are the foundation of modern technology. As we look to the future, periodic trends will continue to guide scientific discovery. From developing new medicines to exploring space, understanding how elements behave will remain essential. The periodic table is a roadmap for innovation. We've covered a lot today, from atomic size to ionization energy and how these trends shape the periodic table. By visualizing these patterns, you can better understand and remember them. Keep exploring, stay curious, and let the periodic table guide your journey in chemistry. Thank you for joining this visual exploration of periodic table trends. We hope you now have a clearer understanding of atomic size and ionization energy and how these trends help explain the behavior of elements. Keep learning and discovering the wonders of chemistry.